Here is a scenario. Consider a horizontal spring attached to an object having some arbitrary mass. Is the force experienced by the object a constant force? Let us recall that the work done by a constant force is equal to F multiplied by D. So we have work done equal to F times D. But in a practical sense, the concept of constant force is very oversimplified. Most of the forces that we encounter in the real world are variable forces. For example, electrostatic force, magnetic force, spring force, all of these are examples of variable forces. In the beginning, when we considered the spring being stretched and released, when the spring is in the stretched condition, it will exert some force on the object to bring it back to its original shape. This force is called the restoring force and is dependent on the distance moved by the object from its initial position. That is why F is equal to negative of x, or we can say that force, the restoring force, is a function of the displacement. Now, let us calculate the work done by such a variable force. For our ease of understanding, we are going to consider the stretch happening in only one dimension. When a variable force is acting on an object that displaces it from its original position, let's say xi, to another position, let's say xf, then we can say that work is done by that force to move from xi to xf. This work done is equal to the area under this curve. So here we have a curve between force and displacement, and the area under the curve will tell us the total work done. This area is not easy to calculate because the shape of this curve is irregular. Therefore, we are going to consider a tiny strip or a tiny rectangle here, which is corresponding to a small displacement, that is delta x, for which the force can be considered constant. Now, we can divide this area into several of these tiny rectangles, each having a thickness equal to delta x. Now, this small amount of work done is equal to the area of this small rectangle. So that can be written as delta W is equal to Fx times delta x. The total work done by this variable force can be calculated simply by adding up all the areas of these individual rectangles from xi all the way to xf. As the small displacement delta x approaches 0, the number of individual rectangles will keep on increasing without limit. However, the total value of the work done, or the total value of the area, will be equal to the area under this curve. Therefore, we can conclude that the work done by a variable force can be expressed as a definite integral of the force over the given displacement from xi to xf. Now that we have calculated the work done for a variable force, we shall try to prove work energy theorem for a variable force. First, let us recall the work energy theorem for a constant force. It states that the change in the kinetic energy of a particle is equal to the work done on it by the net force. So Kf minus Ki is equal to W. So now we can tackle the work energy theorem for a variable force. The work done by a variable force f of x is obtained from the relation W is equal to the definite integral of fx dx over the interval xi to xf. So we understand from our earlier work that this energy is converted into kinetic energy based on the work energy principle. So we can say that the rate of change of kinetic energy is equal to d by dt half mv square. So dk by dt is equal to mv times dv by dt, or in other words, F is equal to m times dv by dt. Force is mass times acceleration. So we can substitute this value in the earlier relationship to come to the conclusion that dk by dt, that is the time rate of change of kinetic energy, is equal to F multiplied by v. Now, since v is velocity, that is the rate of change of displacement with time, v is equal to dx by dt. Hence, dk by dt is equal to F times dx by dt. Therefore, we can prove that Kf minus Ki is equal to W. That is, the work energy theorem for a variable force holds true for both constant and variable forces. So what is the link between Newton's second law of motion and the work energy theorem? The Newton's second law of motion relates the force and acceleration of an object to a particular instant in time. While in the work energy theorem, it is an integral form of Newton's second law of motion that involves an integral over an interval of time. While the second law of motion is in vector form, the work energy theorem is in scalar form. So let us summarize.
Manorama Horizon. Learning made simple.